This is a video lesson on part 16B and 16C. 16B is on radiosensitivity. Going back to the cell cycle, mitosis, which is the most radiosensitive stage in this cycle, and that's because there's the most action. It's going through prophase, metaphase, anaphase, and telophase. The S phase, which has the longest phase of the whole cell cycle, is the most radioresistant for that reason, because it takes so long to go through that stage. There are two types of cells which are identified by their rate of proliferation and their state of development. The first type are immature cells. They retain the ability to divide and they divide rapidly. These cells are generally more sensitive to radiation than mature cells. The other names for these cells are precursor, stem, and undifferentiated. Mature cells no longer divide, or they divide at a slower rate than immature cells and are less radiosensitive. These are known as N cells or differentiated. So radiosensitivity of cells, something very important is for us to take a look at this list of looking at the most radiosensitive cells to the least. The most radiosensitive cells in the body are the lymphocytes, which are in charge of immunity, the spermatogonia, which is in the 2N stage of spermatogenesis, which is in the very beginning part of it, erythroblasts, which are embryonic red blood cells, intestinal crypt cells, which are cells that line the small intestines, the endothelial cells, osteoblasts, which are embryonic bone cells, spermatids, which are in the end stage of spermatogenesis, toward the end of it, but not quite there, right before spermatozoa, fibroblasts, and then muscle cells, which are myocytes, and then finally the least sensitive cells in the body are nerve cells. So radiosensitivity of cells and tissues are determined by the location of the organ in the body, the rate at which the cells mature in the organ, and the inherent radiosensitivity of the cell type. Let's take a look at radiosensitivity of cells and organ systems. So lymphocytes and erythroblasts are have very high radiosensitivity in the human body. So therefore, the hematologic system is the most radiosensitive system in the body. Intestinal crypt cells are the fourth in the list, and that means that the gastrointestinal system is going to be the middle, or it's going to be the next sensitive system in the body. And then because nerve cells are the least sensitive cell in the body, the central nervous system is also the least sensitive as well. In terms of organic damage, we're looking at the radiation-induced damage at the cellular level can lead to measurable somatic and genetic damage in the organism as a whole. And so somatic damage is going to be somatic damage to somatic cells. Examples would be cataracts and leukemia. And genetic damage would be damage to genetic cells, which an example there would be Down syndrome. Now let's go to 16C, which is Fundamental Principles of Radiobiology. So ionizing radiation, exactly what is that? That's radiation that causes ionization, which is damage. And ionization can occur with electromagnetic radiation, which are X-rays and gamma rays, or particulate radiation, which includes alpha particles and beta particles. Keep in mind that absorption results in ionization, which leads to damage. So the law that we are to talk about here is dealing with radiosensitivity of living tissues that varies with maturity and metabolism. With this law, we know that stem cells are more radiosensitive and mature cells are radioresistant. Younger tissues and organs are more radiosensitive. Tissues with high metabolic rate are radiosensitive. And a high proliferation rate for cells and a high growth rate for cells result in high or increased radiosensitivity. Physical factors that affect radiosensitivity include LET, RBE, and fractionation with protraction. So LET is the measure of the rate at which energy is transferred from ionizing radiation to soft tissue. It's a method of expressing radiation quality and determines the value of the WR, which is the radiation weighting factor. If you have a high LET, you have more ionizations. The LET of diagnostic X-rays is approximately 3 kiloelectron-volt per micrometer. The RBE is the ability to produce biologic damage. Technically, it's the ratio of a standard radiation dose to produce the same response as that following a test radiation dose. The RBE of diagnostic X-rays is a 1. If we look at the relationship between LET and RBE, as we look at 25 megavolt X-ray photons with a 0.2 LET and a 0.8 RBE, compared that with heavy nuclei, which has a 1000 LET, an LET of 1000 and an RBE of 30, there's a directly proportional relationship between the two. So LET can be thought of being absorption, and as you increase absorption, then you increase the effect, or the damage, which is the RBE. Same thing happens here. We're looking at cobalt, which is gamma rays, and the low end of the spectrum, and we're looking at, as we increase the LET, the RBE also increase until you reach that heavy nuclei, which is a region of overkill. So if we look at gamma rays and X-rays have a low LET, which is a low absorption, low ionization. Alpha particles have a high LET. The WR for X-ray and gamma photons is 1, where alpha particles is a 20, showing that it's 20 times more damaging than X-rays and gamma rays. And the RBE is also low for gamma and X-ray because the effect is going to be low. The damage is going to be low, where alpha particles are going to cause a high amount of damage, which is also shown by their WR. Protraction versus fractionation. Protraction is where radiation dose is delivered continuously but at a lower dose rate. An example would be 6 gray delivered at a rate of 2 gray per minute in 3 minutes versus 6 gray delivered at a rate of 10 milligray per hour for 600 hours. Both doses end up being the same, but each one was delivered continuously. Fractionation is where radiation dose is delivered at the same dose in equal portions at regular intervals. An example would be 6 gray delivered at a rate of 2 gray per minute in 12 equal fractions of 500 milligray separated by 24 hours. The benefit of the fractionation is that repair and recovery can occur between the doses, and this is commonly used in radiation therapy. So let's take a look at biological factors that affect radiosensitivity that include oxygen effect, age, recovery, chemical agents, and hormesis. Number 1 is the oxygen effect. Biologic tissue is more sensitive in an aerobic state with oxygen. It has medium sensitivity in a hypoxic state and is least radiosensitivity in an anoxic state, which is without oxygen. So the idea is that if you increase the level of oxygen, we increase radiosensitivity. And if you think about it, diagnostic X-ray imaging is performed under conditions of full oxygenation unless we're going to the morgue. OER is the second item. It's the ratio of radiation doses under anoxic conditions to produce the same radiation responses that following irradiation under oxygenated conditions. The way I think about it, it's the oxygen enhancement ratio, which is is the radiation enhanced by using oxygen. So it is LET dependent. It's a high for low LET radiation, which is a maximum value of 3 that decreases to 1 for high LET radiations. So like I said, OER stands for oxygen enhancement ratio. Gamma and X-rays have a high OER because if we have oxygen, it's going to enhance the effect of using gamma and X-rays. Alpha particles don't care if there's oxygen or not, so alpha particles have a low OER. Age. Humans are most radiosensitive before birth. After birth, sensitivity decreases until maturity. So we are the least sensitive at maturity. In old age, humans become somewhat more radiosensitive. Recovery. Human cells can recover from radiation damage. If interphase death does not occur, which is the death that happens before interphase begins, the cells will recover from sublethal radiation damage. So recovery is equal to intracellular repair plus repopulation. Chemical agents modify the radiation response of cells, tissues, and organs. Radiosensitizers are called sensitizing agents because they amplify the effects of the radiation on the molecule, such as halogenated pyrimidines and vitamin K. Radioprotectors are radioprotective agents, and they've not found human application because they have to be administered at a toxic level. Hormesis suggests that at very low radiation doses, which is less than 100 milligray, that these doses are beneficial. A little radiation stimulates hormonal and immune responses to other toxic environmental agents, and otherwise we practice ALARA. So this is the final part of this section.